Geoscience Australia provides specialist advice, knowledge and capability in response to some of Australia's most important challenges. This includes managing the nation's marine jurisdiction and maintaining geoscience knowledge and capability. Geoscience Australia is supporting the multinational search effort to find missing Malaysia Airlines flight MH370. Its scientific teams provide advice and expertise to Australian government agencies, the Joint Agency Coordination Centre, and the Australian Transport Safety Bureau. This collective effort has enabled the mapping of over 200,000 square kilometres of seafloor in a remote area of the southern Indian Ocean. Undertaking a search in an area of this magnitude, remoteness and complexity is an involved process which draws on multiple techniques, technologies and experts from a range of disciplines. Previous maps of the MH370 search area have been derived from satellite data, only providing an estimate of the ocean depth. Such low-resolution maps cannot safely guide navigation during an underwater search, which requires more detailed knowledge of underwater features. A high-resolution map can be created through a comprehensive bathymetric survey, which collects high-resolution data from the seafloor. Bathymetric data is gathered through the use of multi-beam sonar equipment mounted on a ship's hull. The sonar system sends out multiple sound waves that bounce off the seafloor and return to the ship. The delay between sending and receiving a signal provides a measurement of ocean depth. The strength of the return signal provides an indication of how hard the seafloor is. The ship proceeds through the search area in overlapping lines to systematically capture depth information. Overlapping the lines increases confidence in the accuracy of the mapping and helps to address gaps in the data, which may occur due to factors such as bad weather. Scientists working at Geoscience Australia review, correct and analyse the data to create three-dimensional models and maps that reveal details of the seafloor. Bathymetric mapping during the search for MH370 has revealed a detailed picture of the underwater landscape, identifying potential hazards to navigation within the search area. These include large mountains and deep trenches, some of which plunge to more than 6,000 metres below sea level, along with seamounts and ridges, like this one, which is 34 kilometres long. The bathymetric map is an essential navigation tool for the more detailed underwater search. Using the bathymetric map to safely navigate at a much closer range to the seafloor, the Joint Agency Coordination Centre and the Australian Transport Safety Bureau carry out the underwater search. Search vessels slowly tow a small submersible vehicle or towfish on a cable around 10 kilometres long. The towfish descends thousands of metres down through the water until it travels approximately 100 metres above the seafloor. The towfish operates a side-scan sonar that maps features on the seafloor in much greater detail. It gathers data up to 1 kilometre on either side of its path. The side-scan sonar sends out pulses of sound that reflect off seafloor features. Some types of material, such as boulders, gravel, volcanic rock or metal, reflect the sound waves more strongly than fine sediments like clay and silt. To accurately capture data, the towfish travels at very slow speeds of only 3.5 kilometres per hour. Interpretation of the captured data produces images that resemble black and white photos and reveal a great degree of detail about features on the seafloor. The collection of this highly detailed data aims to identify any crucial evidence of the missing aircraft. Scientists and experts from many and varied disciplines continue to work together to assist in the ongoing search efforts for MH370. The different types of data acquired and analysed through their efforts has proved critical to understanding the environment in which the search is operating. In future, Data from the bathymetric survey will also form a permanent record of this deep ocean and contribute to new scientific knowledge and understanding.
Sonar. Objective: to learn the basic physics of sonar. Sonar is a technique that uses sound propagation to navigate, communicate with or detect objects, usually underwater. The word sonar comes from the first letters of the word sound, navigation and ranging. There are two types of sonar: active sonar and passive sonar. Active sonar involves both the transmission of the sound pulses and receiving the echo of the transmitted sound. Since the speed of sound is constant and fast in water, the distance or depth of an object is found by measuring the time it takes for the sound waves to return after having been transmitted. When sound travels through water and strikes a submerged object, it reflects back. The distance of a submerged object can be calculated by dividing the time taken by the sound waves divided by 2 into speed of the sound. Sound travels about 1500 meters per second through water. Consider sound waves returning after 4 seconds. The sound wave takes 2 seconds to travel towards the object and 2 more seconds to reflect back. Since the sound travels about 1500 meters per second, the total distance traveled will be 1500 meters times 4 seconds is equal to 6000 meters. That is, the sound traveled 3000 meters and reflected back. The depth or distance of the object from the source of the sound is 6000 over 2, which equals 3000 meters. Active sonar can be deployed by helicopters mounted in buoys or on boats. Passive sonar involves listening to the sounds given off by targets. Passive sonar can only indicate the direction in which an object is located, but not its distance. Ships and submarines use passive sonar to locate other ships and submarines. Summary: Sonar is an acronym for sound navigation and ranging. It works on the principle that sound travels quickly with constant speed in water. Active sonar is used for locating submerged objects and to find the depth of an object. Passive sonar is used to find the direction of an object.
Hi, welcome to How to Use Sonar to Map the Ocean Floor. My name's Gwen, and I'm doing this specifically for my 3rd, 4th, and 5th grade science class. Sonar is an acronym. It stands for Sound, Navigation, and Ranging. The important thing to know about sonar is it's man-made, and we use it to calculate distances. Echolocation, on the other hand, is something that animals can do. Echolocation, the animal will send out a noise and it waits to find out how long it takes to return to them, and from that the animal can figure out how far away something is. Marine mammals, cetaceans, such as dolphins and porpoises and whales, actually have a specialized part of their brain, called the melon, devoted to echolocation. A bat also uses echolocation. Now, sonar is useful for a couple of things. For one thing, boats and subs can find out how far away they are from other boats and subs. But what we're interested in here is how sonar is used to map the ocean floor. Here's a map around Maine of an ocean. If you notice, it looks like any old topographic map, but it's of the ocean. The deep blue, dark parts are deep in the ocean. The light cyan blue is higher up. You notice you have circles just like a topographic map. So if you imagine a boat going on this grid, kind of like Battleship, and you can imagine how it can create that map. Now, there's two important facts that you need to know about sound before you can start calculating. The first is that sound travels at a certain speed. It travels at different speeds in air and water. In fact, in water it's 4.3 times faster than in air. In water, sound travels at about 1,500 meters per second. In air, it's 343 meters per second. That's dry air. And in water, it's actually 1,484 meters per second. Now, another important fact about sound is that it travels in waves and it bounces. So if sound travels, hits something, and bounces back. So here's an example calculation. I'm pretending to be the blue dot, and then there's that board or whatever it is, something that's going to reflect the sound. I emit a noise, it travels to the board, it reflects back, and then I hear it. Note that the total elapsed time was 2 seconds. The sound started at 4:20:02. It returned back 2 seconds later. So the distance that this was away, it only took half of that time because the other half was coming back to me. So I'm going to divide that number in two, and I get 1 second. Now there's this equation that you guys probably know. Distance equals speed times time. If you've ever been in your mom's car or your dad's car and they're driving along on the freeway, say they're going 60 miles an hour, and you know that there's 1 mile left, so you know you have 1 more minute before your mom exits the car. My son does this all the time. He figures that out in the car. Well, this is similar, except we've adjusted the equation a little bit. Distance equals rate times time. So to calculate our distance, we know our rate. Remember, that's 1,500 meters per second. That's the speed of sound in water. And we multiply that times our time, which was 1 second. And we end up with 1,500 meters second over 1 second. Now, if you remember your fractions, anything over itself is 1. If you multiply anything by 1, it's itself, and we don't care about it. So 1 second over 1 second is 1, and we can just slash through the whole thing there. We're left with 1,500 meters. So here's some boat. The boat just pinged on the continental slope. It took a second to go there and back. So remember, only half of that time is the time that you need to calculate the distance, because the other half is coming back up to you. Over here, we're over a little mini trench, and the boat takes 2 seconds. Over here is a seamount, and the boat takes 1 second, so it's half a second. Over here, we're over a big trench. Takes longer. Over here is a seamount with a little trench in between it. And then another calculation over here would be for an abyssal plain. The abyssal plain is where all the things in the ocean that die, it's where they go. And that's deep, so it takes longer. Now some trenches are deeper than that. In fact, the Marianas Trench is actually significantly deeper than that abyssal plain. Abyssal plain is usually 3,000 to 6,000 meters deep. So pause here for a minute and try your calculations out. And remember to divide by 2.